All lubricants have a common primary function: to reduce friction between moving surfaces. In the context of engines, this friction reduction slows down component wear and prevents excessive heat from being generated. For a motor oil, there are three additional essential functions: the prevention of corrosion of internal components, sealing, and providing cooling via heat transfer. The ability of an oil to be effective at these functions is directly related to maintaining a stable lubricant film across a vast range of temperatures and operating conditions. A film that is too thin allows for metal-to-metal contact, while a film that is too thick creates excessive internal friction and poor flow. While a broad range of physical properties contribute to a complex overall behavior of a lubricant within an engine environment, they can be categorized into two key modes of lubrication: hydrodynamic and boundary lubrication. In hydrodynamic lubrication, the rapid movement of parts containing engineered bearing features such as journals forces a thick, pressurized wedge of oil between the surfaces, completely separating them and supporting the mechanical load. Under these conditions, the oil's local viscosity at that pressure and temperature is the single most important property. Sufficient viscosity allows the fluid to resist being squeezed out under load, preventing metal-to-metal contact. In contrast, boundary lubrication occurs when conditions do not support a full hydrodynamic film, such as during startup and at low speeds, or under very heavy loads. The oil film thins to the point where microscopic metal peaks can almost touch. Here, the chemical makeup of the oil, specifically its anti-wear and load-carrying additives, becomes critical to prevent scoring and seizure, though this mode of lubrication is easily compromised by contamination and surface contaminants. Smaller, less sophisticated engines that operate without pressurized oil systems primarily rely on this method of lubrication and are particularly sensitive to the load-carrying additives. Motor oils are complex, highly engineered lubricants with their performance characteristics being defined by a spectrum of testing parameters. The most fundamental measurement is known as kinematic viscosity. This test measures the time it takes for a known volume of oil to flow through a calibrated glass capillary viscometer under the force of gravity. It is essentially a measurement of the oil's resistance to flow and is represented in units called centistokes, or square millimeters per second. A higher kinematic viscosity value means the oil is thicker. It should be noted that while there isn't a single all-encompassing oil testing standard, the American Society for Testing Materials International dominates the fundamental test methods that are used across the industry. From these testing standards, other organizations derive their own grading systems for lubricants. In ASTM D445 kinematic viscosity testing, two specific temperatures, 40 degrees Celsius and 100 degrees Celsius, are used to create a basis for comparison. The concept of an oil weight is derived from kinematic viscosity measurement. Established as a simplified grading system by the Society of Automotive Engineers, this system categorizes viscosity ranges at 100 degrees Celsius for standard weights and at 0 degrees Celsius for winter or W ratings. For kinematic viscosity, an oil's viscosity index is determined. This dimensionless number, typically determined by ASTM D2270, quantifies how much an oil's viscosity changes with temperature, with a high viscosity index signifying that the oil's viscosity changes relatively little as temperatures fluctuate. This is generally a desired characteristic of an engine oil. Motor oils are also tested at the limits of their operational envelope. The ASTM D4683 standard outlines the procedure for measuring a lubricant's high-temperature, high-shear viscosity. The process utilizes an instrument called a tapered bearing simulator, which heats a small oil sample to a constant high temperature of 150 degrees Celsius. While held at this temperature, the oil is subjected to a high shear rate by being spun rapidly within the tight clearance between a fixed stator and a rotating rotor. The instrument measures the amount of torque required to maintain the rotor's speed against the oil. This torque measurement is then used to calculate the oil's dynamic viscosity, with the final result being reported in centipoise, or 1 millipascal second. At this point, it's really clear that engine oils depend entirely on an understanding of complex interactions that most people never see. This is conceptually quite similar to back-end development in our software-driven world, and that actually brings me to the sponsor of today's video, boot.dev. Every app and website you use has a back-end that does all the heavy lifting. If you've ever been curious about how those systems work, or if you're looking for a career with amazing earning potential, you need to check out boot.dev. Personally, I use a lot of Python to drive some of the tougher visuals on these videos, and I've been spending time on the platform myself to make sure it's something I genuinely recommend, and it's fantastic. Boot.dev has cracked the code on how to learn software development because they tackle the biggest problem with online learning: boredom. They believe you can't learn to code without actually writing a ton of code and building real projects. This isn't about memorizing, it's about learning by doing. From the very first lesson, you're working on mini projects and writing code directly in an integrated console in your browser. You can learn everything you need for a career in backend development with courses in Python, Go, JavaScript, SQL, and more. If you get stuck, their AI assistant, Boots, uses the Socratic method to guide you with questions instead of just giving you the answer. So if you're a hands-on learner who wants to build a real skill, I can't recommend it enough. Head to boot.dev and try out the courses for free. If you love it and want the full experience, you can use my code to get 25% off your entire first year on an annual plan. And now back to oil. Dynamic viscosity effectively measures the internal resistance of a fluid to flow when a force is applied. When a breakdown in viscosity under mechanical stress occurs, this is known as oil shearing. At the other end of the operational envelope is cold cranking oil performance. The ASTM D2602 cold cranking simulator apparent viscosity was developed to best evaluate this condition. This test is conducted in a manner similar to the high temperature high-shear test, though with a 3-minute coolant cool-down cycle from room temperature before the rotor is spun for 1 minute. The resultant RPM is compared against reference oils to determine an accurate representation of the apparent cold cranking viscosity in centipoises. In addition to viscosity response, another common mechanical test of engine oil is the 4-ball wear test, or ASTM D4172B. This test measures the wear preventative characteristics of a lubricating oil. The test consists of 3 fixed steel balls and 1 rotating steel ball placed on top of the fixed balls. The balls are set into a bath of the oil being tested, and the test is ran, typically for 1 hour at a specific load and RPM. The constant friction between the rotating top ball and the 3 stationary balls creates circular wear marks on the 3 lower balls. The diameters of the 3 wear scars are measured and averaged. A smaller wear scar indicates better anti-wear performance. A more intense variant of the wear test is the extreme pressure properties, or EP test. Defined by ASTM D2266, the procedure is similar, but instead of a constant load, the test applies a series of progressively increasing loads for short durations, with the goal being to find out the weld point, where the friction heat becomes so intense that the lubricating film breaks down completely, causing the 4 balls to weld together. Beyond mechanical properties, motor oils also go through a range of chemical reactivity tests that quantify how it responds within a combustion environment. These include the pour test, which defines the lowest temperature at which the oil will still flow. This is critical for cold climate startups. A similar low temperature metric known as the borderline pumping temperature is also determined. This is the point at which viscosity is so high that the engine is not capable of turning over fast enough to start. This metric is used by automotive manufacturers to determine the oil grades for low temperatures and the respective required cold cranking amperage capacity. The flashpoint test determines the temperature at which an oil's vapors will ignite, indicating its volatility. The NOAC volatility test determines the percentage of oil lost to evaporation at high temperatures. A lower NOAC rating signifies less oil consumption and fewer harmful deposits. The acidity of an oil is also determined through the total acid number test, which measures the amount of acidic material in an oil, which can increase as the oil oxidizes and degrades in service. The complementing total base number test measures the oil's reserve alkalinity, or its ability to neutralize harmful acids from combustion. A higher total base number allows for longer service life. Engine oil also undergoes foaming tendency tests as excessive foaming from agitation can lead to problems such as starvation at the oil pump inlet and a breakdown of hydraulic component operations such as valve lifters. Ultimately, the carefully selected properties designed into an oil begin to break down the moment it's put into use. The useful life of a motor oil within an engine is directly determined by its resistance to a handful of modes of degradation. Oil oxidation is the most significant form of chemical breakdown for engines. Caused by the continuous reaction with oxygen and residual water inside a hot engine, this results in highly reactive acidic compounds that lead to corrosion, changes in oil viscosity, and the formation of deposits, varnish, and eventually sludge. These oxidation byproducts create a cascade of future damage, causing piston rings and valves to stick, and potentially clogging oil passageways. Deposits on pistons are especially harmful because they inhibit heat transfer and can lead to combustion irregularities such as preignition and detonation. To combat this, oils are first protected through a refining process that removes naturally occurring chemicals prone to oxidation. Engineered additives called antioxidants are also blended in to improve resistance, but these additives get used up over time, after which the oil oxidizes rapidly. Creating an oil involves a critical balancing act, as the refining process that improves oxidation resistance also removes natural compounds needed for boundary lubrication and require engineered additives to restore this lubrication. When an engine oil is heated beyond a certain temperature, it will start to degrade, even with no oxygen present. This is called thermal degradation, and it causes the oil to change viscosity over time. While it is not possible to increase thermal stability through additives, much like boundary lubrication, it can be increased by limiting the amount of oxidation-resistant compounds in the refining process, adding another point of consideration to the formulation balance. Beyond reactive degradation, shear forces created by the intense mechanical stresses within an engine are constantly tearing an oil's molecular structure apart. While this effect primarily affects viscosity-modifying additives, such as those used in multigrade oils, this effect causes the oil to permanently lose viscosity, and its viscosity index decreases, while its ability to resist wear is reduced. Multi-viscosity petroleum oils are the most susceptible to this type of breakdown, while straight-weight petroleum oils are less affected. Synthetic motor oils, however, are extremely resistant to the damaging effects of shear forces. Oil shearing is the primary reason many small, hot-running engines like those in lawnmowers recommend straight-weight petroleum oil, because their intense heat and load can shear the viscosity improver additives found in multigrade petroleum oils, preventing it from achieving its intended viscosity. Beyond the oil's physical properties, contamination from dirt, soot from combustion, unburnt fuel, and wear metals continuously compromise the oil's integrity. Fuel dilution is particularly problematic as it lowers the oil's viscosity, reducing its ability to protect engine parts. All engine oils are made from the heavier, more viscous portion of crude oil that remains after the more valuable, lighter fractions like gasoline, diesel fuel, and kerosene have been removed through distillation. The bulk of a typical motor oil consists of hydrocarbons with between 18 and 34 carbon atoms per molecule. These base oils are categorized into 5 distinct groups based on their refining process and chemical properties. Group I base oils are the most basic, solvent-refined mineral oils. They are typically a mix of different hydrocarbon chains with little uniformity, and they're suitable for less demanding applications. Group II oils are more refined through hydrocracking, offering better oxidation properties, though they only offer fair performance in areas like pour point and cold crank viscosity. These are common to conventional mineral-based motor oils. Group III oils are even more severely hydrocracked, resulting in a purer base oil with a good molecular uniformity and a high viscosity index. It's important to note that Group III base oils are not chemically engineered, but are commonly mixed with additives and marketed as lower quality synthetic or semi-synthetic products. Group IV base oils are the basis for modern high-performance synthetic lubricants. These synthetic base stocks are not refined from crude oil in the traditional sense, but are instead built from the ground up through precise chemical reactions, with the most prevalent base being polyalpha olefin, or PAO. PAOs are created through a multi-step synthesis process called oligomerization, where smaller, double bonds containing alpha olefin hydrocarbon molecules are chemically joined together to form larger, more uniform polymer chains. The resulting PAO is then hydrogenated to remove any remaining double bonds, which significantly enhances the polymer stability. The result is a base oil with a highly consistent and branched molecular structure, free from the undesirable elements found in conventionally refined mineral oils, such as sulfur, nitrogen, and waxes. PAOs exhibit a naturally high viscosity index, maintaining its viscosity over a much wider range of operating temperatures. Also, the absence of wax and the branched molecular structure give PAOs a very low pour point, and their stable saturated molecular structure makes them highly resistant to breaking down under high temperatures and oxidation. This translates to longer oil life and reduced formation of sludge and deposits. When these high-performance base stocks are combined with a carefully balanced package of additives, the final product is a lubricant with exceptional performance, a stable chemical composition, and a long service life. The development of fully synthetic oil began in the 1930s in both the United States and Germany for use in demanding military applications such as jet engines. The transition to consumer vehicles was pioneered by AMSOIL, which introduced the first synthetic motor oil to meet API service requirements in 1972. Mobil Oil further propelled synthetic oils into the mainstream with its national launch of Mobil 1 in 1975, establishing the foundation for modern synthetic engine lubricants. Beyond the primary base stocks, Group V forms a catch-all category for all other base oils not included in the first four groups, such as esters and polyalkylene glycols, or PAGs. These oils are generally not used as base stock but as a blending additive to enhance the properties of other base oils. For the vast majority of engines, base oils have too narrow of an envelope of effective physical and chemical properties and require an array of additives to extend their usability. One of the most common and critical additives are viscosity index improvers. This category of additives has been the basis for the emergence of multi-viscosity oils in the 1950s, and even today, modern engines simply wouldn't exist without them. Multi-viscosity petroleum oils are manufactured by starting with a lower viscosity base stock oil and blending in long-chain polymers designed to stabilize oil performance across varying temperatures. The most prevalent examples include olefin copolymers, or OCP, and polymethyl acrylates, or PMA, and high-stability styrene-based copolymers. At cold temperatures, the viscosity improver molecules remain tightly coiled and have little effect on the oil's viscosity. As the oil heats up, the polymer molecules uncoil and expand. This expansion counteracts the natural tendency of the base oil to thin out, making the oil behave like a heavier weight oil and maintaining a protective film on engine parts. These large polymers, however, are highly susceptible to breakdown over time from oil sharing. Anti-wear additives are another common addition to oil blends and are primarily used to protect the engine during boundary lubrication conditions. When a full oil film cannot be maintained, one common additive, zinc dialkyl dithiophosphate, or ZDDP, for example, decomposes under heat and pressure to form a sacrificial glass-like phosphate film on metal surfaces. For more severe conditions, with extremely high loads such as in gear oils, extreme pressure or EP additives are required. These compounds, often containing sulfur-phosphorus chemistry or organometal compounds like molybdenum dithiocarbamate, or MoDTC, that react chemically with the metal surfaces only at the point of intense pressure, forming a resilient boundary layer that prevents welding and scuffing. Zinc dialkyl dithiophosphate also functions as an anti-corrosive additive, protecting ferrous metals from acids formed during combustion. This is often supplemented with metallic detergents like barium sulfonates and calcium phonates that also neutralize acids and form protective surface barriers. Oxidation inhibitors that slow oil degradation are another common additive. The two primary types of antioxidants are hindered phenols, which are effective at moderate temperatures, and aromatic amines, which provide excellent protection at very high temperatures. They work by interrupting the free radical chain reactions that drive oxidation. Several categories of additives are designed to improve an oil's mechanical characteristics. Detergents and dispersant additives, for example, manage the byproducts of combustion. Detergents are metallic compounds, commonly calcium sulfonate or magnesium phonates, which neutralize corrosive acids and help keep hot engine components free from deposits. Dispersant additives are organic polymers like polyisobutylene succinamides that keep solid contaminants like soot, sludge, and oxidation products suspended in the oil, preventing them from settling on engine surfaces. Dispersants work in conjunction with the oil filtration system to keep solid contaminants out of the lubrication system. Anti-foam agents are commonly added to reduce the surface tension of the oil. These additives are typically silicon polymers like polydimethylsiloxane that are insoluble in the oil and attached to air bubbles, creating a weak point that causes them to rapidly collapse, preventing foaming. On conventional petroleum-based oils, pour-point depressants, or PPDs, are added to initiate the formation of paraffin crystals at low temperatures. A commonly used depressant is polymethyl acrylides, or PMA, or styrene esters that co-crystallize with the paraffin wax and interrupt their crystallization structure as it forms. Engine oil service specifications are established by a cooperative of global industry organizations, with these being periodically updated to address advancements in engine technology, emissions, and regulations. In North America, the development of these standards is primarily managed by a tripartite system consisting of the Society of Automotive Engineers, which identifies the need for new or updated specifications, the American Society for Testing and Materials, which is responsible for developing the precise testing methods and parameters, and the American Petroleum Institute, which licenses and markets the final oil classifications to consumers. The API's classification system remains one of the most widely recognized globally and is divided into two primary categories: the S series for service, covering gasoline engines, and the C and F series for commercial diesel engines. The progression of S categories reflects the evolution of passenger car engines, with each new standard offering backwards compatible enhancement. The current SP specification focuses on high-temperature deposit protection, sludge control, and addresses issues seen in turbocharged and direct injection engines. The diesel engine oil classifications have evolved significantly to handle increased soot levels from exhaust gas recirculation systems and to protect sensitive after-treatment devices like diesel particulate filters. Current specifications focus on fuel economy and are not backwards compatible like S categories. Recognizing the specific need for passenger cars, U.S. and Japanese automakers formed the International Lubricant Standardization and Approval Committee that established more responsive and stringent standards, particularly concerning fuel economy and the long-term durability of emissions control systems. ILSAC standards designated by the GF series often align with the latest API S category but include additional requirements, with the most recent designations being established for lower viscosity, high-efficiency engine oils. The European Automobile Manufacturers Association also developed its own oil sequences for European vehicles, which are often more stringent than API or ILSAC standards. These are divided into categories for passenger car gasoline engines and light-duty diesel engines, catalyst-compatible oils for vehicles with particulate filters and catalysts, and heavy-duty diesel engines. Engine lubricants are a vast and complex topic that is continuously evolving, and while we've only scratched the surface of their fundamental properties that make them an integral part of engine design, the intricate balance of these basic parameters are what allows modern engines to meet the demands of higher performance, increased efficiency, and long-term reliability.